안녕하십니까. 빠메온 교수님 지도하죠. 박사과정 공부하고 있는 다원권입니다. 오늘 졸업반 비율은 한국말로 설명 자문합니까? 영어로 발표하겠습니다. Today, I would like to present about my dissertation, a study on the development and operational characteristics analysis of a saturated iron core superconducting fault current limiter in the DC power system. This is the content of my talk. It starts from the background and motivation, and then conceptual design of the SI-SF cell in the DC power system. And next is the design and fabrication of lab-scale SIF cell in the DC power system. And next, an operational characteristics analysis of the lab-scale SIF cell. Finally, the discussion and conclusion. Let's start with the study background. In recent years, a high voltage DC power system based on the voltage source converter have been widely developed and utilized worldwide. However, one of the major challenges of this system operation is to limit and block the DC fault current. In the voltage source converter based DC power system, when the fault occurs, the IGBT immediately block for the cell protection. At this time, the capacitor voltage is higher than the AC side three-phase voltage. So the DC side is the capacitor discharge into the short circuit point. The capacitor discharge rapidly and cause very high fault current, which can be great dangerous for the capacitor and the diodes. Moreover, when the capacitor voltage drop to the 0 voltage, the last AC three-phase short circuit will occur. So the DC circuit operation must be operated in this capacitor discharge state. About the background of the SFCL in the DC power system. Unlike AC system, in the DC system, the current now have a zero crossing point, so it's very difficult for the conventional circuit breaker cut off the last short circuit for current. Therefore, a current limiting device is required to limit the DC fault current to relatively low level. A superconducting fault current limiter with superconducting property can significantly limit the fault current and reduce the stress on the circuit breaker for the DC power system. This slide shows the investigation of high capacity DC circuit breaker development in the world. The main parameter of a DC circuit breaker is the breaking current level and breaking time. The current design circuit breaker can break the fault current up to 40 kiloampere with a time less than 10 milliseconds. This is the survey result of the 100 publication on the DC SFCL. Most of study have developed the SFCL for the high voltage DC power system, but this were only simulation analysis study. Experimental study only in the medium and the low voltage level. The fault limitation rate were achieved an average value of 70%. Recently, most of the DC SFCL study focus on the resistive and saturated iron core types. The resistive SFCL is most simple and compact design, thus limit the fault based on the properties of the superconductor. However, it only has advantage to use in the low voltage system. In case of HVDC system, the voltage over 100 kilovolts, the resistive SFCL is not applicable due to the current manufacturing technology of the STS wire. Not like resistive SF shell, the saturated iron core SF shell using the iron core properties to change the inductance to limit the fault. So the current not directly follow the superconducting coil, so no quench occurs. Therefore, the SIF shell is more suitable for the high voltage and high capacity DC power system. In this dissertation, the author developed a conceptual design of the SI-SF shell for the distribution VSC-based MVDC power system, and then a lab-scale prototype SIF shell was designed, fabricated, and tested to confirm the effectiveness of the SIF shell through the experiment. The SIF shell was designed with the targeted fault limitation rate of higher than 70% and the fault limitation time higher than the 10 milliseconds. Next section is the conceptual design of the SIF shell in the voltage source converter based MVDC power system. Based on the Capco distribution system range from 40 MVA to the 70 MVA, the author selected 45 megawatt DC power system and model the 50 kilovolt 3 kiloampere DC power system for the SI-SF shell conceptual design. The basic system parameter like cable impedance and DC link capacitor of this DC system were already determined. Also, the fault current characteristics of this DC system were simulated and analyzed. This graph shows the fault current level according to the fault distance point. At the result, you can see the longer distance, the lower fault level, the lower fault current level achieved. Next, I would like to talk about the design configuration of the SI-SF shell. Basically, SI-SF shell include one primary copper coil and an iron core and a secondary superconducting coil. In the normal operation, the secondary coil will fully saturate the primary side with the opposite magnetic field. So at this time, the inductance will be very small because air core inductance. And when the fault occurs, the current increase very fast, and this core side is out of the saturation. So the inductance increase and limit the fault. After fault clearing, the SI-SF shell can immediately recover because of no quenching on the superconducting coil. Before starting the design of the SI-SF shell, a detailed design process will be built. Firstly, specification of the DC power system, including the rated voltage, the rated current, rated power, and the fault current level were determined. And then the core material was selected from the core properties and the DC grid parameter. The calculation of the core dimension and the core design were implemented. Finally, the BSCAD EMTDC simulation model were built to analyze the fault current limiting characteristics, the design targets, and the selected configuration of the SI-SF shell were shown here. In the detailed design process, firstly, the initial first step, the initial parameter of the VSC-based DC power system will determine the maximum fault current level without the SF shell operation is 14 2 kiloampere. In the second and third step, the parameter of the iron core and the core system will determine. The SIFCL can design like a transformer. The iron core dimension is calculated based on the rated power of the DC grid, and number of turns of the coil system and the operating current of the secondary coil can be calculated from the magnetizing property of iron core and the fall duration. Selected fall duration. After define the own parameter, the BAK simulation model will simulate and confirm the operational characteristics of the desired SIFCL. As the result, so here in the normal operation, the secondary coil will fully saturate the primary side with the opposite magnetic field, and then you can see the primary inductance is very small because air core inductance, and when the fall occurs, the primary side core will out of the saturation, and the inductance increase very fast up to the 0.37 Henry. And here is the fault current limiting performance result. Comparing with the case of no using the SFCL, using the SIFCL could limit the fault up to 70.4% with a limitation time of the 12 milliseconds. So the design target of the SIFCL were already obtained. In order to demonstrate the effectiveness of the conceptual design as well as the performance of the SIFCL through the experiment, a lab scale SIFCL was designed in detail with the same target before, based on the mathematical model and the initial parameter of the lab scale SFCL were determined by and shown in this table. In the practical design of the SIFCL, the loss is a very important factor. We can reduce and affect and reduce the magnetic energy during the transient fault. Thereby, it can reduce the inductance as well as the fault limit capability of the SIFCL. There are three main loss in the SIFCL, including the copper loss in the primary coil and the iron core loss and eddy current loss in the coil bobbins. So next step, I will design the iron core and the coil system based on the loss and the material cost problem. In the first step, the iron core was designed to minimize the eddy current loss and the hysteresis loss. The laminated structure was selected to minimize the eddy current loss. In case of the hysteresis loss, we can select the core material like carbon steel or silicon steel to minimize the hysteresis loss. Considering the core material and the core properties, three core types, including the medium carbon steel, non-oriented silicon steel, and oriented silicon steel, were investigated and analyzed. Three core types were designed with the same dimension and structure like that. It was constructed by the lamination module stacked on each other. We need to determine the number of modules because the silicon steel is very thin lamination. So the number of lamination modules were determined for the S45 core. As the result, you can see the number of the last module number greater performance of the SIFCL. Finally, the 10 lamination module were selected. In order to analyze the electromagnetic properties and the operation of the SI SFCL, a 3D FEM simulation model were built. The voltage source converter DC power system with the 4 condition circuit were also integrated in this simulation model. And here is the result of the fault current without the SIFCL in the FEM simulation. The fault limiting characteristics of the SIFCL with recall material were analyzed and compared by using the FEM simulation. In the theory, the SIFCL limit the fault based on the transient inductance of the primary coil. So we can calculate this value based on the transient voltage and transient current. As a result, the fault you can see here, the fault limit of the SIFCL with recall ties were no significantly different. The limitation rate were higher than on case were higher than 70%. But considering the material cost, we selected the S45 core and the M36 core to manufacture, test, and compare in the experiment. So next is the design of the secondary superconducting coil. 3 ATS wire tie with the different properties and the cost were considered, including the Cernam, TIVA, and the PASF, with the same target of the fault limitation of 70%, the shear margin of the 20%, and the operating temperature of 77 Kelvin. The coil design, the number of turns, and the critical current were determined in this graph. The summary and the comparison of the secondary coil with the 3 kinds of the ATS wire was shown in this table, with the same design targets of the SIFCL. Considering the wire cost, the Cernam wire is the most suitable, and I selected it for the secondary coil fabrication. And this slide shows the detailed design specification and structure of the secondary coil. The circular shape double winged coil were applied. There are 3 DBC with 50 turn each DBC. It will go out on the aluminum bobbin. So the question is why we use the aluminum bobbin in the secondary coil. The reason, the aluminum bobbin like a single turn coil that separate the secondary coil from the magnetic changing in the iron core during the transient fault. Thereby, it can reduce the induced current and the induced voltage in the secondary coil. So as you see in the simulation result like this, using the aluminum bobbin, it can the induced voltage and the induced current was greatly reduced during the fault. Because there was induced current in the bobbin, so it caused eddy current loss. Like this. In addition, the aluminum bobbin didn't affect to the fault limit capability of the SIFCL, was shown in this graph. In case of the copper primary coil design, a 2.8 millimeter diameter enameled copper wire was selected. It can withstand a current up to the 64 ampere. So there is no problem with the normal current of the 50 ampere of the DC system. In the bobbin design, the material and the structure were considered to minimize the eddy current loss. Based on the cost and material properties, 3 kinds of bobbin were considered, including the aluminum solid bobbin, the aluminum cutting bobbin, and the GFRP bobbin. Here show the fault limit performance of the SIFCL according to the primary popping type. The higher eddy current loss of the aluminum bobbin, solid bobbin, significantly reduce the fault limit ability of the SIFCL. In case of GFRP bobbin, there were no eddy current loss, so the fault limitation, you can see, very good. However, the GFRP material have a very high cost compared with the aluminum. Therefore, I suggested using the aluminum cutting bobbin to reduce the eddy current loss as well as the material cost of the primary bobbin. After design the own component and the lab scale SIFCL were fabricated. Firstly, is the iron core system. Here we selected the two types of iron core, S45C and M36 core. They already was manufactured and assembled. In case of the primary coil, it was wound on the 3-kind bobbin at the design. The parameter of primary coil was measured and compared with the FEM simulation. So at the result, you can see the measurement result and the FEM simulation were similar. The coil inductance was measured by the LCR method with a different frequency. From this result, we can see the effect of the eddy current loss in the metal bobbin to the coil inductance. With the higher frequency, the higher eddy current loss, so greatly reduce the coil inductance. That's the reason why the aluminum bobbin, solid bobbin have a low performance for the fault current limit. Next is the secondary coil fabrication. It will wound on the aluminum bobbin and co-winding with the Kapton film. After winding, the critical current and magnetic field were confirmed when cooling the coil in the liquid nitrogen. All the measurement results are summarized in this table. You can see they were similar to the FEM simulation result. Next session is the experimental test and operational characteristics analysis of lab scale SIFCL based on the principle of the voltage source converter based DC power system. A simplified experiment circuit were developed. In principle, normal operation, this circuit breaker will close, so the normal current of the 50 ampere will follow the SIFCL. When the fault occurs, this circuit breaker will open. So AC side is the isolated and the DC side is the capacitor discharge, cause a very high fault current. And here is the fault current result in the experiment compared with the FEM simulation. This is the equipment of the fault testing system and measurement system. In the fault testing, the fault limit characteristics of the SIFCL were confirmed with the different secondary operating current and then compared with the FEM simulation result. As you see, the experiment result was similar to the FEM simulation result. With the secondary current of 200 ampere, the fault current was limited up to 73.6%. During the fault test, the induced current and the voltage in the secondary coil were quite low, which didn't affect to the DC bias current source and secondary coil operation. Next is the performance analysis of the SIF cell with the different coil design. Firstly, the primary coil with a different bobbin design. The fault limit performance with 3 kinds of bobbin was shown in this graph. Using the GFRP bobbin, you can and aluminum cutting bobbin, you can see the SIF cell already achieved the design target. However, the GFRP bobbin could reduce the current rising DIDT better than aluminum cutting bobbin. So it can increase the fault limitation time compared with the aluminum bobbin. This slide summarize and compare the characteristics of the SIF cell with the three kinds of the primary bobbin. In detail, you can see the aluminum cutting bobbin not only has good performance similar with the GFRP bobbin, but also significantly reduce the induced current and the voltage in the secondary coil. Especially, it have a much lower cost. So its bobbin type is the most effectively to use in the practical SFCL design. Next section is the performance of the SIF cell with the 2 kinds of the iron core. We'll test and compare. At the result, you can see using the M36 core, the SIF cell could limit the fault better than using the S45 core, but the difference is not big. As a summary in this table, using the S45 core, the SIF cell could achieve a design target like that, and significantly reduce the core material cost comparing with the M36 core. One more advantage you can see here. The S45 core could reduce the induced current and induced voltage in the secondary coil, thereby it's more advantage to design the protection for the secondary coil in practical design. For all the above experiment result, the code analysis of the SIF cell with different design was implemented. At the result, you can see the SIF cell using the M36 iron core and the TIVA wire in the secondary coil, and using the GFRP bobbin in the primary coil have a highest code, and the total code in this case was set to 100% for comparison with the other case. In case of in this case, the SIF cell have a lowest code when using the F45C iron core and using the Cernam wire for the secondary coil and using the aluminum cutting bobbin for primary coil. The total code could be reduced up to the 46.3% compared with the highest case. The finally additional experiment, the lab scale SIF cell were tested in coordinating with the real DC circuit breaker, mechanical circuit breaker. The full testing system were developed and were fabricated like this. The DC power supply is constructed by the battery system consisting 63 battery in series. It will supply the voltage of the 500 volts for the fault current state. In the normal current of the normal current is 50 ampere. So the range of the fault current can be from the 500 ampere to 5 kiloampere. The fault duration of the circuit breaker have has the range from the 3 millisecond to 500 millisecond. This is the equivalent circuit of the testing system. The fault current and the DC and circuit breaker operation without the SFCL operation will confirm first. You can see the circuit breaker can trigger at 140 ampere and break the fault current after 3 milliseconds. The target of using the SFCL is to reduce the breaking current of the circuit breaker. The operating characteristics of the SFCL were tested and compared with a resistive SFCL module. Like this, there was in case of using the resistive SFCL, it need time to increase the resistance during the quench. So there was a very large source current here from the starting. Therefore, the circuit breaker can detect the fault and break more faster. It's very fast. However, the last source current like that is very dangerous for the power system. In case of using the SFCL, because it have a last inductance, so the last inductance can reduce the current rising DIDT. So there was no the surge current from like a resistive SFCL, because reduce the DIDT, so the circuit breaker can detect and break the fault current more slower. You can see especially the saturated FCL can greatly reduce the breaking current level, compare much more than the resistive FCL. So here it can limit the fault up to the 70%, and in case of the resistive, only the 53%. Next session is the discussion in the future work. Through the own implemented experiment, the operating characteristic and high performance of the SFCL with the different design options were confirmed. In the MVDC and HVDC power system, the induced current and voltage in the secondary coil are very high, which can damage and the DC bias source secondary coil and may affect to the fault current limit performance of the SFCL. So protection method must be carefully considered in the practical design of the SFCL. By applying the aluminum cutting pop pin in the primary coil, aluminum pop pin in the secondary coil, and laminated iron core, we can reduce the cost and the complication associated with the protection design of the secondary coil. The problem of eddy current loss can also be applied to the optimal design of the iron core system. In the future, I plan to design a large-scale SFCL for the real 30 kilovolt, 1 kiloampere MVDC power system. Final is the conclusion. This dissertation presented the design and fabrication and the operating performance analysis of the SFCL in the DC power system. A conceptual design including the configuration, design process, and mathematical model of the SFCL were implemented in 15 kilovolt, 3 kiloampere DC power system. Then the operating principle and the fault limit characteristics of the design SFCL were analyzed in the PSCAS EMTDC simulation. In order to demonstrate the effectiveness of the conceptual design as well as the performance of the DC SFCL through the experiment, A prototype lab-scale SI SFCL was designed in a 500-volt 50 ampere DC power system. The target of the fault limitation rate and the limitation time was set at to the 70% and 10 milliseconds respectively. The optimal designs of the iron core and the core system were proposed. A 3D FEM simulation model was built to analyze the magnetic properties and the fault limit characteristics of the SI SFCL and compare with the experiment result. Experiment circuit of the SISCL were developed for the fault condition test and coordinating with the circuit breaker. As a result, the SISFCL had a high current limiting capability, reducing the fault magnitude up to the 70.6%, and the fault limitation time could achieve 21 milliseconds. So the design targets were already obtained. With the design of iron core pop pins in the primary and secondary coil, the induced current and voltage in the secondary coil were reduced quite low. So the fault current did not affect to the DC current source and secondary coil operation. The SIFCL was successfully tested with the circuit breaker. It could reduce the breaking current up to the 70%, especially it significantly reduced the rising rate of the fault current DIDT and allowed more time for the DC circuit breaker operation. The results obtained in this study can be effectively applied to large-scale SI SFCL development study for the MVDC or the HVDC power system. That's all my dissertation presentation. Thank you for your attention.